Hello everybody, I'm Mark Michelson, a senior software engineer at Red Hat and a member of the core OVN development team. As you can tell by several of the talks at this conference, performance and scalability has been a big topic for OVN in the past year, and I'm here to share some information from the perspective of a Red Hat developer. Why was performance such a big focus in 2021? First off, it may seem obvious, but everyone likes their software to run faster. This goes even more so when it comes to the transparent back-end processes like the control plane of the network. From Red Hat's perspective, OpenShift wants to use OVN as its default SDN solution. Up until early 2021, the main concern had been feature parity with OpenShift SDN. But even with all the features in place, nobody wants to use OpenShift if the network performance has decreased. When trying to improve performance, it's important to note that test numbers will change depending on the target topology. Since we're targeting OpenShift, and by extension OVN Kubernetes, this is the target topology. I don't expect everyone to grok this diagram right away, but there are a few key things to point out. Each node, or hypervisor if you wish, contains a single logical switch, with a variable number of pods attached. There's a single logical router, called the cluster router, that connects the nodes. Northbound, a single join switch connects the cluster router to the gateway routers that reside on each node. Now in the diagram, it appears that there are multiple join switches, but really is just one these days. Each of these gateway routers connects to another node-specific EXT switch that then connects to the underlay. With this topology, there are several components that factor into its performance. First, OVN Kubernetes defines the topology and relays commands between Kubernetes and OVN. OVN then programs the desired logical network into OVS. In the midst of this, the OVS DB is used as the data store both between OVN Kubernetes and between ovn-northd and OVN controller. Therefore, each of these components needs to be operating at their best. Han Zhou is giving a talk that touches on some of the OVN Kubernetes improvements, and Ilya Maximets is giving a talk about OVS DB. For this reason, for this presentation, I'll focus solely on OVN. So how do we test things in OVN? First, we could mimic the test topology using OVN Heater and OVN Tester. OVN Heater is an application written by Dumitru Chara that allows for quick setup of an OVN test cluster across multiple hypervisors. Lorenzo Bianconi and other Red Hat developers wrote OVN Tester and added it to OVN Heater to allow for logical topologies to be applied to the cluster created by OVN Heater. This allowed for us to run tests that isolated OVN and OVS DB so that we could focus on improving those. When we wanted to involve OVN Kubernetes, we made use of Kind, Kubernetes and Docker, to simulate a Kubernetes cluster using Docker containers. Finally, the performance and scale team at Red Hat ran tests on OpenShift clusters. For more targeted tests, we could write shell scripts in the OVN sandbox that ensured the improvement we wrote was actually helpful. But in the end, those will be put through OVN Tester as well to ensure that they made a positive impact on the overall system. Now, the initial baseline tests did not go well, but I'll save the details for those tests until the end of the presentation. This is the point where I could go into a detailed timeline of what fixes went in at what point and give a week-by-week illustration of how OVN improved over time. But that's terribly boring and I'd run over time. So rather than doing that, I'll break the issues down into observed categories and then provide some specific examples of those and how they were fixed. First off, while the bottlenecks seem to ping-pong between different OVN components, it seemed most consistently to be in the central components, that is ovn-northd and the OVS databases. During our testing, we observed that the number of logical flows in OpenFlow flows was quite high. Even if we were able to tweak algorithms in OVN, reducing the number of flows was a surefire way to decrease CPU and memory usage. Sometimes an innocent-seeming piece of code in one component might result in a different component having to perform more work than expected. And finally, if you wanted to single out an OVN feature as being pure evil, load balancers fit the bill perfectly, since they do all of the above and have their own unique set of performance issues. Let's dive into an ovn-northd issue. In general, ovn-northd didn't see any groundbreaking single changes, but rather had many small improvements that added up. For this example, let's discuss an algorithm used to calculate ARP request flows on logical switches for reachable and unreachable addresses. Reachable addresses are DNAT or load balancer VIPs that are assigned to a logical router and that lie within the gateway router port's configured subnet. Unreachable addresses are those that lie outside the subnet. Our algorithm for unreachable addresses had previously started by iterating over the logical data paths in their ports first. Then an inner loop would iterate over all load balancers, building logical flows as necessary. Analysis showed that this was not especially expedient, especially since the number of load balancers in our test scenarios was much, much larger than the number of data paths. Lorenzo Bianconi came up with an elegant solution. Swap the loops. Now ovn-northd first loops through the load balancers and then the data paths. This rather simple change managed to take the ovn-northd loop time for a test case with 121 logical routers, 241 logical switches, and 47,000 load balancers down from about 12 seconds to about 9 seconds. That counts for about a 25% speedup. Not bad. Let's look at an example where we were able to reduce the number of flows. One of the philosophies of OVN has been to try to avoid tunneling when possible. This means that we tend to program many duplicate flows across all nodes so that traffic can be kept local as much as possible. However, if tunneling is inevitable, then it makes no sense to duplicate the flows on all the nodes. Hans Zhou identified that OVN Kubernetes could use distributed gateway ports to connect the node switches to the cluster router. Then he did the difficult work of writing a fix that would analyze the topology and ensure that data paths would not be considered local if it lay beyond the DGP boundary and did not require distributed processing. This particular change had tremendous results. For his test, he created an OVN Kubernetes-like cluster with 1,000 nodes, each with 10 logical switch ports bound. Then he created 2 port groups, each with 2,000 logical switch ports. Then he created 10 stateful ACLs that regulate the traffic between the port groups. The results speak for themselves. There was a 70% decrease in the number of flows programmed per node, an 80% decrease in OVN controller memory, a more than 90% decrease in the OVN controller recompute time, and an over 90% decrease in the OVN controller restart time. Now let's look at something that in isolation seems smart, but when inspected as a part of the whole ends up being bad. Touching on unreachable addresses again, we used to combine all of the flows into a single logical flow. After all, the actions for each individual logical flow were identical. The only thing that changed was the destination IP address. This seems like a smart idea since it reduces the number of logical flows to 1 for a given data path. It's important to note that even though there was only 1 logical flow, this would expand into many open flow flows. This wasn't a surprise. However, analysis showed an unexpected side effect. We use a logical flow cache to ensure that we do not need to reparse logical flows that we parsed in a previous OVN controller loop. When unreachable addresses change often, then the single logical flow changes often too. This means our logical flow cache entry gets invalidated frequently. When the logical flow cache entry is invalidated, we have to recalculate all of the OpenFlow flows associated with the invalidated logical flow. For cases like we have seen previously, there may be tens of thousands of unreachable addresses. This means we could be recalculating that many OpenFlow flows per OVN controller iteration. Dumitracharya realized that a solution to this was to use separate logical flows for each unreachable address. This resulted in a larger number of logical flows, but it also resulted in much less churn in OVN controller. Now if we add a new unreachable address, say a new load balancer VIP, then it means only having to calculate a single OpenFlow flow instead of potentially thousands. Here are some results for a test that used 120 nodes, 250 logical switch ports per node, and 2,500 load balancer VIPs. The total logical flows went up, much as expected, since the single logical flow per data path increased. However, the total size of the southbound database went down due to interactions with data path groups that I didn't go into previously. But the stat to really check out here is the OVN controller recalculation time. It went down by about 98% from this one change. It's definitely a case where the increase in logical flows was worth it. Load balancers have come up a couple times already in previous examples, but here is a time where we can showcase a very load balancer specific problem all on its own. OVS databases are sometimes set up so that a row in one table might have a reference to another row in another table. This typically is very helpful, since if the reference row is updated, then the rows that reference that row are also marked as updated as well. However, in some cases, it turns out that this is not actually the behavior we want. In this particular case, logical flows keep a reference to logical data paths, and logical data paths keep a reference to load balancers. This means that if load balancers get updated, say to add a new VIP, then that means the data paths that reference that load balancer get marked as updated, and all logical flows for that data path also get marked as updated. This results in invalidating the logical flow cache entries for all of the logical flows and having to recalculate all of them. Dumitru-Char recognized that this was 100% not necessary in this particular case. There's no need for the data paths or logical flows to be updated when a load balancer changes. The southbound database schema was updated so that data paths contain raw load balancer UUIDs instead. This way, when load balancers update, it does not cause the chain reaction it previously did. To prove this change's merit, a cluster with 120 nodes and a single load balancer with 16,000 VIPs was created. Then a new VIP was added. Prior to this change, the OVN controller execution time after adding the new VIP was about 39 seconds. After the change, the execution time dropped to about 8 seconds, an 80% speed up. To sum up the OVN effort, let's put things in perspective. During the time between versions 21.06.0 and 21.09.0, there were 208 commits made to OVN. Checking the release notes for 21.09.0 on the OVN website, there are 21 notable performance improvements listed in OVN. That doesn't include small tweaks that don't merit a mention on the website. Then if you consider that many of the improvements were multi-commit series, my very rough estimate is that around 40% of the total commits for 21.09.0 were enhancing performance. Now let's finally give some overall numbers for our test improvements. For this, I'll be using the Red Hat Performance and Scale team's test parameters and their results. All tests were run at two scales, a scale that is common for OpenShift clusters, 20 nodes, and a medium scale 120 node cluster. All tests initially start by bringing up the cluster with 10 pods per node. The first test variant is the node density light test. This one is simple. After the base cluster is brought up, we then scale up to 250 pods per node. I've done the calculation for you, and that's 5,000 total pods for 20 nodes and 31,250 pods for 120 nodes. The pods in these tests are running a sleep workload. Next is the node density heavy test. For this one, we'll be creating nodes and services. Services in OpenShift translate to VIPs in OVN load balancers. These days, a service has a direct one-to-one correlation with an individual OVN load balancer. For these tests, the pods created are PostgreSQL databases and clients. At 20 nodes, we create 2,500 databases and 2,500 clients. At 120 nodes, we create 6,250 databases and 6,250 clients. Finally, we create an equal number of services, so 2,500 for 20 nodes and 6,250 for 120 nodes. And here are the results. The table here shows how early results compare to current results with 21.09.1. One clear trend is that back in July, density light tests gave dramatically different results depending on the scale. However, with 21.09.1, the pod latency barely increases even though the scale has gone up sixfold. The density heavy numbers tell a different story. First, a couple things need explanation. For 120 nodes density heavy, the initial test by the Performance and Scale team did not complete. This test was not attempted again until October when many performance changes had been put in place. This is why the result is from October instead of July. For 20 nodes density heavy, there was no test run with 21.09.1. The estimate in this column is conservative based on the change seen at 120 nodes. In all likelihood, this number is actually much lower. It's clear that once load balancers are added to the equation, the pod latency increases dramatically compared to a cluster with no load balancers. However, it's also clear from the 120 node tests that we have improved drastically. But we're not done yet. We still have things we can improve. First off, as the previous slide showed, we can still make improvements around load balancers. While testing on 120 nodes was nice, there are much larger clusters out there, and so we need to increase our scale testing to 250 and 500 nodes. Most of our performance tests were centered around OVN Kubernetes topology. With the testing tools we now have, we could also craft new tests that use different topologies to see how those perform. And probably the biggest elephant in the room is to try some larger ovn-northd changes. That's a topic on which an entire talk could be made, and probably has. Thank you very much. It's been a pleasure to present.
Hello, there's Mark's talk. Mark, are you available to answer questions?
Yes, I am.
Excellent. Good to talk to you. It's been a while. We don't have any questions posted yet. Do you have anything to add to your talk before we start seeing some?
No, I guess the biggest thing I would say is just thanks to everyone who made such a concerted effort to make OVN perform better over the past 6 months or so, because it's absolutely been amazing what we've been able to do.
So one thing that I didn't notice in your talk is there an overall goal? Is there a point at which we I don't know declare victory, or is that too far away, or is it just not an interesting question?
So one thing I'll say about the performance and scale team at Red Hat is it's never good enough. And I mean that in a very nice way. What I mean is they'll never settle for this is good enough. So we're always trying to make it better than it currently does. And they will respond by doing larger scale tests to make sure that we're still staying on top of things. So in that sense, I can't say there's a goal. We have been doing comparisons to the old OpenShift SDN implementation to see how pod latency compares to it. And the problem is I'm not 100% sure what the range of, I don't know, error is with our comparison to it, but we're trying to get close to what it could do with the understanding that we probably won't do exactly the same as it did because it didn't have the central components in the same way that OVN does.
That makes that makes sense. It's always a difficult to compare performance tests. The what I've noticed is that in some cases there just isn't a performance goal because you do want it to just be as fast as possible. Open vSwitch is kind of an example of that. You can make it as fast as possible and to use as little CPU as possible, but the goal is zero. People want there to be zero overhead on the CPU, which isn't realistic, but you want to get as close to it as you can. And that I suppose to an extent that's true for OVN as well.
I totally agree with you. I mean, everyone would love for it to be a completely invisible process they never have to think about. And so we'd love to get there as much as possible, but it's we're still working on it. It's a work in progress still.
Yeah, as is most software out in the world today. We got one question in the chat, but it was about your recording. I think that we answered that, and I'll just remind everybody listening that we will post all of the we'll post all of the videos and all of the slides to the conference website after the conference, so everyone will have a chance to watch these again if you like. So now it's